Hey everyone, my name is Ido, and I was the CEO of CTS Labs during 2017 and 2018. My friend over here is Uri. He was the head of research in our company during the same time. In this talk, Uri and I are going to tell you about extensive research we've done over the time period on AMD processors. So on March 2018, we published an advisory revealing multiple critical security vulnerabilities in AMD processors. Our advisory talked about 2 sets of vulnerabilities, summing up to a total of 13 flaws. The first set of vulnerabilities in our advisory involved the AMD chipset. Now, for those of you who don't know, the chipset is an I/O controller that's installed as a separate chip on the AMD motherboard, and it houses inside of it multiple controllers, such as a USB controller, a SATA controller, and a PCI Express bridge, and some others as well. On Ryzen systems, the chipset is powered by an internal Intel 8051 architecture microcontroller. The second set of vulnerabilities, which is also the main part of our research, revolves around the platform security processor. The platform security processor is AMD's version of Intel's management engine. So I'm going to talk extensively about the PSP today, but before I delve in deeper, I would like to start with a quick demo. And I'm going to do this demo on this machine that we had in our office. It's a Ryzen desktop machine. So you're looking at an RDP connection to an AMD Ryzen machine. I just open up in the video read write everything. For those who don't know, read write everything is a tool that allows you to read and write physical memory and to play with hardware devices. Now, what you're seeing over here on the screen is a memory mapped I/O address that I opened. There are 2 registers over here. And the second one, which is a 64-bit register, is, it points to a buffer in physical memory. And I just opened the buffer over there to the right. Now, on the memory mapped I/O, I put a value here into this register. And you can see a string appeared on the right side of the screen. Now, this string that you're seeing comes directly from a small ARM chip that exists inside every AMD processor today. That chip is the platform security processor. Until recently, the inner workings of the platform security processor and the exact scope of its capabilities has been mostly unknown. But after 8 months of research in our company, we've got lots of interesting things to share with you. So in this talk, we're going to talk about why the PSP and its security are important, how we conducted security research on the PSP, and finally, we're going to show you 3 of the most interesting vulnerabilities we found. So the PSP is an independent ARM Cortex-A5 core that's been integrated into AMD processors and runs its own operating system. In essence, it's a security subsystem similar to Intel's management engine or to Apple's Secure Enclave. The PSP was introduced in 2013 primarily to function as an immutable root of trust to verify the integrity of the BIOS before the computer boots up. This is done in order to prevent malware from loading up early in the boot process. In 2017, with AMD's release of the new Zen architecture, they added a whole new world of functionality into the PSP. These days, the PSP is a trusted platform module. It also manages encryption of physical memory pages, and it supports loading up third-party trustlets, which makes it extensible. So, for example, the PSP could be extended to support something like digital rights management, or, as another example, you could add support, let's say, for intrusion detection. Now, the PSP is a highly trusted and very powerful component. When an AMD machine is turned on, the PSP component responsible for giving the PSP is the component responsible for giving the main processor permission to boot. The first instruction that executes when you power up an AMD machine is not an x86 instruction, but an ARM instruction inside the PSP. The PSP only allows the main processor to boot after it's verified that digital signature of the BIOS is OK. This puts the PSP at the base of a long chain of verification, where each component verifies the next, making sure that every piece of code that runs during boot time is digitally signed. Without the PSP, there would be no one to check the first piece of BIOS that gets to run. So that would make the beginning of the BIOS a very good place to install malware. The PSP also functions as storage for encryption keys. It contains firmware-based implementation of TPM that is used by the operating system. So for example, if you're using BitLocker and you have disk encryption on an AMD machine, your encryption keys are most likely stored inside the PSP. The PSP also has complete unrestricted access to main memory. It can access any location in RAM at any time, including protected regions such as system management mode or virtual machine address spaces. And as far as we saw, it also can do that disregarding any IOMU configuration that the BIOS might have done. Finally, the PSP is completely independent from the main processor. It runs regardless of whether your OS is running or not, and you can only communicate with it through a limited and well-defined interface. This makes the PSP a very good place to hide malicious code. If you can control the PSP, you can circumvent many important security features such as TPM and virtual machine isolation. And if you could patch the PSP firmware, you could create very powerful malware that's virtually impossible to detect or to remove. Because of all of this, the PSP has been a source of controversy in the open source community. The main argument against it is that it's a black box. It's a closed source, undocumented chip that has complete control over your system. You cannot shut it down, you don't know what it's doing, and you don't know what's running on it. So it's a fairly scary prospect. To make matters worse, the PSP exists on almost every new AMD product on the market today. Desktop PCs, servers, laptops, GPUs, you name it. All of this makes the PSP a very valuable target for hackers, which is also why we were interested in looking into it. So with that, let's dive a little bit into PSP internals. The first thing we're going to do is we're going to show you how to locate the PSP firmware and understand how it's built. Then we're going to show you how to take control over the PSP in several different ways. And finally, we're going to demonstrate how all of this could be used practically in the course of a cyber attack. Let's begin by locating the PSP firmware. What you're looking at is one of AMD's marketing slides about the PSP. One thing that stands out is the sentence, secure off-chip non-volatile storage for firmware and data, that is SPI ROM. This implies that the firmware for the PSP resides on SPI Flash. Incidentally, that's also where the system BIOS is stored. So our first step was to go to our motherboard manufacturer's website and download a BIOS update. So we got a BIOS update, and we open it up with UEFI tool. Now, if you haven't heard about it, UEFI tool is a very useful tool for viewing and editing BIOS images. Looking at the output on the screen, we see a list of GUIDs representing UEFI volumes. In between the GUIDs, you can see padding sections. On most BIOS images, these padding sections are empty. But on AMD BIOSes specifically, some padding sections are not. So we opened up a padding section, and we found something interesting inside. We found the word PSP. Next, we used binwalk to analyze the padding section and found ARM instructions inside. That was a very good sign that we're looking in the right place. So we took the padding section and we put it in IDA, and we got nice and clean ARM code. So after we found the firmware, we set a goal to ourselves to achieve code execution on the PSP. We didn't care how we do this, or whether or not it required any physical modification to hardware. And the reason we wanted to do this so badly is because we knew that would allow us to understand the inner workings of the PSP by way of debugging and trial and error. The problem was the PSP was designed to prevent us from doing exactly that. Let's take a look at the PSP boot process to understand why that is. The PSP implements a strict chain of verification, digital signature verification. When you power up the AMD processor, the PSP boot ROM is executed first. As implied by the name, the boot ROM is read-only, meaning it's code that is fabricated into the processor during manufacturing. The boot ROM's job is simple: to check the signature of the first piece of firmware that gets to run, and then, if everything checks out, to run it. That particular component is the PSP bootloader. Generally speaking, the PSP firmware is organized in a file system structure. The firmware contains many different modules, and each one of these modules is individually signed by AMD. The first thing the boot ROM does is to parse a data structure on SPI Flash called the PSP directory. That is the file system structure that you're seeing in the illustration on the screen. From there, the boot ROM can locate the AMD public key, which is then used to verify all the other PSP modules. The public key itself is verified against a secret HMAC value that's manufactured into the CPU. The next step for the boot ROM is to use the AMD public key to verify the PSP bootloader. And if the bootloader passes verification, it loads the bootloader into RAM and it executes it. At this point, the firmware begins to run. The bootloader, which is the first component in firmware that gets to run, goes ahead and loads many other components that exist inside the PSP directory. For example, one such component is the PSP operating system. Before letting the components run, however, the bootloader verifies their digital signature against the AMD public key. So again, everything is signed and verified. Eventually, the bootloader also verifies the BIOS signature. And if the BIOS signature checks out, the PSP releases the x86 cores from their initial frozen state. And that allows the computer to start. So without that, the computer is basically stuck. So you can see there is a whole chain of verification starting at the PSP boot ROM and going all the way to the BIOS. Later on, the BIOS verifies the OS verifies kernel drivers, and that's how you get secure boot. Let's take a deeper look into how exactly the PSP verifies digital signatures. I mentioned earlier that the firmware is organized like a file system, and that every file or module contains its own digital signature. The PSP loads these modules on demand, and modules can contain either ARM code or they can contain configuration data. Before loading any module into memory, however, the PSP does signature verification. If verification fails, the PSP enters an infinite loop. Because the x86 cores are still frozen during that time, the system is stuck. And this is how essentially the PSP prevents us from making changes to its firmware. If you take a look at individual modules, you would see that each one of them contains a header and a body. And you would also see that at the end of the module, there is a digital signature attached. Because the header and the body are hashed and signed together, if you make any changes to either one of them, it would break the signature and the system won't boot. Let's look at a real-world example. What you're seeing on the screen is the header of the PSP bootloader module. Two particular fields are marked: the total size of the module and the size of the area that's digitally signed. The latter one should cover, just a second. Okay, so the number of bytes specified on the latter one, signed part size, is the number of bytes that gets hashed into the digital signature, meaning that's the header and the body. Now, you would expect that signed part size would be large enough to cover the entire module, except the signature area. But what happens if it's not? So what we did next was we crawled the web and we downloaded every single BIOS for every AMD board ever released. We then wrote scripts to extract and check all PSP modules to see if we can find discrepancies between these two sizes. And guess what? As soon as we ran the script, we discovered interesting things. We found specific modules where assigned part size was 0. When we looked closely into these modules, we saw that they do not contain code. They contain something that looks like either settings or configuration data. It turns out that consistently for data modules, signed part size is 0. Yet these modules do contain a digital signature. But if signed part size is 0, what exactly is signed? So after some checking, we found that the signature in these modules only covers the header. I mean, why would you want to sign data anyway? So let's think for a second what we got here. We've got a perfectly valid, correctly signed PSP module with an unsigned body. What happens if you replace the body in the module with code? The answer is, it runs. So, for example, we could replace the PSP operating system with this module and give the PSP our own OS, which is exactly what we did, and it runs perfectly. So this allows us to inject code into the PSP and take over it before even a single x86 instruction gets executed. So let's recap. The PSP controls the boot process. As part of the boot process, PSP loads modules from its firmware, and each one of those modules is digitally signed. But some modules out there are incorrectly signed, and if you could find one, you could use that module as a placeholder for malware. So all you have to do is get one of those modules, put malware inside, put that module in place of a legitimate module, and during boot, that module is going to pass verification, and your code is going to get to run. It's pretty simple. So I'm going to show you a demo of this attack that we've done against an Epyc server in our office. On the right, we have an Epyc server, and on the left, we have an HP laptop that's logged into remotely into the server. What we're going to do first is we're going to take our modified BIOS update, which contains our patched PSP module, and we're going to flash it on the server. Then we're going to restart the server. Now the server is booting. Look closely at the bottom right corner of the screen. Thank you. So the postcodes you're seeing are coming from the PSP. So we've managed to get unsigned code running on the PSP, and that gave us a lot of visibility into PSP internals. We also wrote our own Python debugging interface for the PSP, and we used it to do a lot of investigation into how the PSP works. And we found many other interesting things inside. So with that, Uri's going to share some of them with you.
Thank you. All right. So in this section, I'm going to talk to you about another interesting attack surface that the PSP has, and that is the Mailbox interface. And the Mailbox is basically a way to send the PSP commands. And for example, if you remember this image from the start of the talk, that's an example of how we sent the get version command to the PSP through this Mailbox interface to get the version of the firmware that's currently running on the PSP. So this Mailbox interface is mostly intended to be used by the BIOS during the system boot. And it has three main use cases. One is to query the PSP for information. Second is to initialize some systems in the PSP. And the third is related to power management. So for example, when the computer needs to enter sleep mode, it needs to tell the PSP that it is through a Mailbox command. So there's this set of commands that you can send the PSP, and as we've demonstrated, you can just do it from a simple Windows program. So obviously, this is a very interesting attack surface. So in the next couple of slides, I'm going to first give you an overview of how the Mailbox works. And then I'm going to show you some bugs and design mistakes that exist in some of those commands and how you can use them to bypass security features and in some cases even gain code execution on the PSP. So first about how Mailbox works. Basically, you have a set of registers that the PSP exposes to memory mapped I/O. And when you want to send a command to the PSP, you write a command number to one of the registers, then you write to physical memory the arguments to that command, and then you supply the PSP with a pointer to the arguments for the command. And on the other side, the PSP has a process that continuously polling for new commands. So if it sees a new command, then it handles it and it writes back the results to the same shared buffer in RAM. So this is a partial list of the commands you can send the PSP, and we actually got this from a header file that we found as part of the core boot project. That's open source BIOS. And it's there because AMD did some contributions to that project so they can have like very limited basic support for the PSP. So we have some information there that we can use. And I'm going to talk about some of the commands that we can send. And the first one I'm going to cover is command number 8. And this command is pretty simple. This command accepts as input an address in physical memory and a size. And then it takes that block of memory and computes some kind of HMAC on it. And it returns as a result a 32-byte HMAC and writes it to the end of the buffer you supply it. So that's pretty simple. And what we can do with this command is basically we can ask the PSP to compute this HMAC on some arbitrary location in physical memory and give it back to us. But what about memory locations that we shouldn't be able to access from a Windows program? So some example of that is system management mode memory. And another example is, what if I'm running inside a virtual machine and there's a second virtual machine in that same hardware, and I shouldn't be able to access the second machine's memory? And an example of that is credential guard. So I'm going to give you a bit of background on credential guards for those who don't know. Credential guard is a technology by Microsoft that's designed to prevent credential theft, so someone stealing your password hashes or Kerberos tickets. And back in the day, when an attacker got a hold of your computer, the natural thing to do was to dump LSAS memory and just extract password hashes and Kerberos tickets and use that to spread throughout the network. And Microsoft wanted to stop this, so they designed this technology that isolates credentials to a separate virtual machine. So if you have credential guard enabled, when you start up your computer, a hypervisor is started that creates two separate virtual machines. The first is called VTL0. It's just running Windows. And the second virtual machine, called VTL1, is running a customized kernel that secures your password hashes and other credentials. So if an attacker gets code execution on your machine, he's not going to be able to extract those credentials because they're isolated by hardware. But the PSP sits at the hardware level. So it has full access to physical memory, including VTL0 and VTL1, and it's not aware of any hypervisors or virtual machines. In fact, not only it has access to VTL1, it needs to have access to VTL1, because if you remember, the PSP is running a firmware TPM on top of it, and TPM is responsible for a lot of storage of encryption keys and encryption operations, and VTL1, the credential guard, makes a lot of use of the TPM. So essentially, the PSP needs to be able to access that memory. So what if we were to ask the PSP to compute an HMAC and give it as input a location that belongs to the second virtual machine, to credential guard? Well, the PSP will gladly do it for us. But this is not obviously interesting because there's this HMAC that's being computed, but we don't know the secret key to that HMAC. So we got this blob back and not sure what we can do with it. But there's a small trick we can do that's going to make this more useful. So what if we ask the PSP to compute an HMAC on a single byte? Well, then we get a 32-byte HMAC that corresponds to that single byte. But what if you build a translation table for every single byte possibility? Well, then we can just query the PSP and give it a location, for example, in VTL1 for a single byte, and then we can convert that to the original byte. And by doing this repeatedly, without knowing actually the secret key, we can dump entire blocks of memory. And taking this a step forward, we can use this trick to dump the whole VTL1 memory and extract whatever passwords and hashes and Kerberos tickets that exist there. So this is a pretty interesting example of how the PSP can be used to cross security boundaries. Thank you. All right, the next thing I'm going to talk to you about is a different command, and it's going to be a little more complex. This command is called smm-info, and what it does is it's responsible for initializing this communication channel between the PSP and the BIOS. And first I'm going to tell you why they need this communication channel at all, and then I'm going to tell you how we can use this command to cause some trouble. So first, why this communication channel exists. So the PSP doesn't come with its own non-volatile storage, but sometimes it needs things to persist in memory. For example, the TPM that's running on top of the PSP needs to store encryption keys sometimes. And what the PSP does is it uses the system's SPI Flash chip, which is just an external memory chip that sits on the motherboard, and uses it as its persistent storage. And the way it does this is, in order to access this chip, the PSP needs to ask the BIOS to do it for him. So in essence, the BIOS acts as a proxy between the PSP and this external memory chip. And this is done through a mechanism called PSP-to-BIOS, in which there's a shared buffer in RAM through which the PSP just dispatches requests to, read and write requests, and then the BIOS picks it up and carries it out for him. So let's go through an example. Let's say the PSP wants to read from SPI Flash. The first thing it does is it writes a description of that request to the shared buffer. And then in order to let the BIOS know that there's a request pending, it's going to generate a system management interrupt to the CPU. And a system management interrupt basically is an interrupt that makes the CPU immediately stop whatever it's doing and jump straight to system management mode. And then the CPU is going to execute code that's going to handle this request. So once the CPU is triggered, it's going to pick up this request, and then it is going to make the read access to the SPI Flash, and then it's going to write those bytes back to that same shared buffer and raise an interrupt back to the PSP, and the PSP is going to read that result. So now that we know what the PSP-to-BIOS is, let's go back to the smm-info command. So as I said, smm-info is used to initialize this communication channel, PSP-to-BIOS, and it does it by supplying the PSP with two things. First, it tells the PSP where this shared buffer in RAM is. And the second thing is it provides a way for the PSP to generate an SMI. And next I'm going to show you how the PSP uses this information to generate a system management interrupt. So as part of the smm-info command, the PSP gets the SMI trigger info struct that you can see on the screen. And this struct contains two key pieces of information. First, it contains the location in physical memory. And second, it contains a bitmask. And when the PSP wants to generate an SMI, it's going to apply that bitmask to that location in memory, which is basically just flipping some bits in that location in memory. And that is going to magically generate an SMI to the CPU. So let's go quickly over the fields that are in this struct. So as part of the smm-info command, we have address, which is just the address to apply the bitmask to. Then we have type, which is always 1. Next, we have value size, which is used to calculate the size of memory to apply the bitmask to. And then we have AND-mask and OR-mask that are the bitmasks to apply to generate the SMI. So for example, AND-mask is used to clear some bits in that address, and then OR-mask is used to set some bits in that address. So we control all of these fields because we can send the smm-info commands ourselves. And let's just look at how the PSP handles this command quickly. So this handler is pretty simple, and this is not PSP code. This is just code that I converted to C from the ARM code that runs on the PSP. All this handler does is basically takes the data from the smm-info command, and it copies it to PSP memory to initialize its own structures. Nothing very interesting, so there's no much attack surface there. But let's see how the PSP uses this information to generate an SMI. So this is a piece of code from the PSP firmware that I've converted to C. And this is basically called for every PSP-to-BIOS request that happens. For example, if I send a TPM command to the PSP, and it needs to access SPI Flash, it's going to invoke this routine, which is going to generate an SMI. And what this code does is very simple. It basically takes the data that was set with the smm-info command, and it uses it to do the same operation I described earlier, to apply the bitmask to that location memory, which is going to generate an SMI. But there's a problem in this code somewhere. So let me go over this code line by line. Let's see. The first thing this code does is it takes SMI trigger info, and then it sanity checks value size and to make sure that it's 4. And if it's not 4, the code is going to error out. Next part, the PSP uses that same expression to calculate size, and thus size can only be 4. And then the next thing, the PSP maps trigger address, which is the address in physical memory, into the PSP address space. And the last part, the PSP reads the current value in trigger address, and he applies the bitmask to it, and then it writes back the new value back to memory. And if you look closely, you can see that as part of the memcopy operation, there's a copy of size bytes into a variable that can only hold 4 bytes, but that should be fine because size can only be 4 bytes, right? We have that if statement. But value size is actually dereferenced twice. Once when it's sanity checked at the beginning of the code, and the second time when size is calculated. And let me remind you that the PSP has a separate process that's always polling to check if there's a new mailbox command. So what if we were to send an smm-info command again, and we time it just right, that it's going to arrive just after this check has been done, but before size has been calculated? Well, we can then switch value size after it's already been checked, and then value size can be anything we want. And we can set value size to something like 8, and then size will end up being 256. And then when we reach the first mem copy, it's going to copy an arbitrary amount of bytes from a place in memory that we control directly into the PSP stack. And this is going to trigger a stack overflow, which is going to be very easy to take advantage of, because the PSP doesn't have any exploit mitigation, no stack cookies, no ASLR, and nothing like that. So what we're going to do to exploit this bug is very simple. We're going to have a Windows program that's going to have 2 threads. The first thread is going to continuously send TPM commands, which is going to invoke this flow. And the second thread is going to repeatedly send SMM info command, and eventually the timing is going to be just right, and we're going to have this stack overflow. And next we have a demo of this vulnerability to achieve code execution on the PSP. And in this demo, we're going to patch some code inside the PSP firmware to make a Mailbox command return some interesting output. All right. So first, I'm going to run this script, which is going to win this race condition a couple times. And this is a multi-stage payload, so it's going to win this race actually like 3 times. And after a couple of times, it's going to succeed. And it's going to get code execution on the PSP and patch some firmware code. All right. So next, we're going to open read-write everything again. And now we're going to run the get version command once again. And let's see what we get this time. All right, this time we got CTS Labs. All right, for the next part, I'm going to hand it over to Ido.
So after all of this, we asked ourselves, can these flaws be used practically in a cyber attack? And the answer is yes. And here is just one example. So Uri mentioned earlier Microsoft's solution against credential theft called Credential Guard. And he mentioned Credential Guard puts passwords and encryption keys outside the reach of attackers by placing them on a separate virtual machine. If you've ever been part of a red team, you must have used Mimikatz, whose author is somewhere in the crowd, to steal credentials. And if you haven't, let's see for a second what happens when you run Mimikatz on a machine with Credential Guard enabled. Wait. Oops, I pressed. Yeah, okay. Do note that this CMD is actually a remote PSX connection into the target, and I'm running Mimikatz on it. So you can see the password is missing, and instead we got a meaningless encrypted blob. The key to decrypt that blob is on the other VM, and there is no way for us to get to the key. So again, the idea is to use a virtual machine for segregation, which is enforced by hardware. But what if we had AMDFlaws? It turns out you can create a bypass for Credential Guard in 3 simple steps. First, we're going to use either master key or Ryzen fault to inject code into the PSP. Then, we're going to use the PSP's highly privileged DMA to inject code into Credential Guard virtual machine. Finally, our solution is going to call an undocumented internal function called LSA ISO decrypt to decrypt the blob that you saw earlier. So we built our own version of Mimikatz that bypasses credential guards on unpatched AMD machines. So let's see this working. So you can see you have the password coming in all the way from the other virtual machine. All right, thank you.
All right. I think we have some Q&A time.
Yeah.
Maybe. All right. I think.
So if you have any questions, we'd be happy to answer.
Yeah, with the mic thing.
Yeah. This research took 8 months, and we had 7 people working on it. Anything else? Yes. We haven't done research into the Intel management engine. There is another group that did that, but I can't really answer it. I read the research a while ago, but we only did AMD research.
Question?
All right, thank you.